This chart tracks enterprise technology. The steep curve is AI innovation. The flat line is organizational governance maturity. This widening gap creates severe regulatory liabilities. Penalties average $2.3 million per incident, and the EU AI Act sets fines up to 30 million euros. These liabilities stem from a mechanical failure in standard enterprise risk management. Most organizations rely on bolt-on compliance methodologies, treating AI oversight as an external check rather than a core engineering requirement. Retrofitting governance after a system is designed creates immediate architectural debt. By the time a model reaches a compliance team for review, the underlying code is locked in. Any required adjustments mean tearing down completed engineering work to inject safeguards that should have been integrated from the start. Modern machine learning deployment pipelines, the automated sequences that compile, test, and release model code, can push updates in hours. But manual legal and compliance reviews often take weeks, creating a severe operational bottleneck. The risks are already materializing in industry failures. A major healthcare diagnostic AI system was recently recalled after systemic bias was discovered post-launch. In another case, a tech firm faced a €500 million GDPR fine specifically for violations in its automated decision-making processes. Retrofitting manual governance is structurally incompatible with the velocity of AI deployment. It transforms a routine product launch into material risk. Expert Ash Masoha argues that effective oversight cannot be an afterthought. It must be architected directly into the technical infrastructure from day one. This requires a transition to continuous AI infrastructure, moving away from the static, manual compliance checklist. This infrastructure embeds governance directly into CI/CD pipelines. CI/CD automates the building, testing, and deployment of code. By placing automated checkpoints inside these pipelines, manual review is replaced by default compliance. To build this automated infrastructure, Masaha developed the four-pillar methodology, a sequential engineering roadmap for reconstructing risk management protocols. First, architectural gap analysis. Second, human-in-the-loop frameworks. Third, proactive risk mitigation. And fourth, practical scaling. Completing this sequence eliminates the operational bottleneck. Oversight becomes a strategic enabler, allowing teams to deploy AI at scale without violating legal guardrails. Teams cannot govern an AI ecosystem they do not fully comprehend. This diagram shows a bare machine learning pipeline wireframe with unlabeled data storage and model training nodes. Before applying any controls, you must establish a baseline assessment of this raw architecture. The first step of the architectural gap analysis is a system-wide inventory. This maps every AI and machine learning model currently in development or production. Next, these models are graded by risk level against regulatory frameworks, specifically matching the categories defined by the EU AI Act. The scan identifies critical infrastructure gaps, such as missing data lineage tracking, which records the origin and movement of data over time, or poor model observability, where developers cannot monitor the AI's internal state or performance. Once identified, the gaps are triaged. Vulnerabilities that pose an immediate regulatory risk are prioritized for rapid remediation, while process improvements are scheduled for long-term optimization. This data translates into an 18-month roadmap. It establishes the technical requirements for the subsequent 3 pillars of the framework. Without a meticulously mapped and classified baseline architecture, automated governance protocols are impossible to systematically engineer. The second pillar integrates human-in-the-loop, or HITL, frameworks. This satisfies the legal mandate for meaningful human oversight, required in high-stakes automated decisions. The engineering challenge is translating an abstract legal requirement into a physical pipeline routing protocol. This graphic illustrates a single high-risk decision node splitting open to reveal a tiered routing structure. We can observe the mechanics of this system through a healthcare diagnostic AI tool. The model evaluates patient scans and suggests diagnoses, but the data must pass through specific oversight channels based on the complexity of the case. In the routine tier, standard AI diagnostic suggestions flow rapidly. They require only surface-level confirmation from a physician before moving forward. High-stakes algorithmic edge cases are forcefully routed away from the routine path. These require mandatory multi-physician analysis at a human override gate. To make accurate judgments, human reviewers must be provided with complete context. Specialized explainability interfaces output the AI's exact reasoning and its statistical confidence levels for each specific prediction. Every interaction at this gate is logged. Continuously tracking these human override rates generates an immutable compliance audit trail, demonstrating to regulators that the oversight is active. Engineered HITL frameworks eliminate the bottleneck of blank check manual reviews while guaranteeing human accountability and high-stakes decisions. The third pillar focuses on shifting risk mitigation left. This means moving compliance interventions upstream into the early stages of the development cycle. This diagram demonstrates the physical placement of automated testing gates. They are situated immediately after model training, but strictly before production deployment. These gates perform specific robustness evaluations. They execute distribution shift detection, identifying when live data diverges from the training data, and run adversarial stress tests to see how the system behaves under extreme edge case conditions. When applied to an e-commerce recommendation engine, the fairness metrics gate tests the algorithm across diverse demographic groups. Models that demonstrate disparate impact on pricing or access are abruptly rejected. At these same checkpoints, data governance controls are enforced. The system automatically verifies data provenance, confirms user consent management protocols, and ensures strict purpose limitation. Establishing clear ethical checkpoints at this phase prevents the introduction of dual use cases, where a benign model could be exploited for malicious purposes, and stops systemic violations of user autonomy. These proactive safeguards function as a continuous feedback loop. Flawed models are rejected back to developers instantly, rather than being flagged weeks later during a manual review. Embedding proactive risk gates directly into the infrastructure catches model degradation and algorithmic bias before they can materialize into financial or reputational damage. The final architectural phase addresses the challenge of volume. The organization must scale this rigorous oversight across the entire enterprise without exponentially multiplying its compliance headcount. This is achieved through governance as code. This diagram illustrates the full pipeline wireframe, now enveloped by an active network that links nodes, gates, and oversight structures. It represents the translation of written regulatory policies directly into automated pipeline triggers. Under this system, technical requirements like bias parity thresholds and documentation completeness are converted into rigid, automated prerequisites. Deployment is technically impossible until the model passes these gates. This automation enables self-service governance, which empowers data science teams to manage their own compliance. Developers are provided with libraries of pre-approved model architectures and automated risk questionnaires. This distributes expertise across the engineering floor, removing the need for a centralized bottleneck. Pushing the rules directly to the engineers allows for instantaneous enforcement. The developer receives immediate compliance feedback on their code in real time. Converting abstract compliance policy into automated executable code removes the friction from risk management. This mechanism separates high-velocity AI organizations from stagnant, liability-heavy competitors. These four pillars are not isolated tasks. Combined, they form a single, holistic operating system for continuous compliance. The business return on investment for this architecture is quantifiable. When a major enterprise software platform transitioned to this framework, the metrics shifted immediately. By eliminating manual governance reviews and replacing them with automated gates, the company reduced its AI feature deployment cycles from 6 weeks down to just 3 days. This dashboard shows the resulting metrics. The platform achieved a 12 times increase in deployment velocity, while simultaneously maintaining a flat line of 0 material compliance violations across hundreds of deployed features. These metrics drastically increase board-level confidence. With systemic risks mathematically controlled, the organization can authorize highly aggressive capital investments into future AI development. Securing both speed and safety simultaneously transforms compliance from an operational brake pedal into a formidable competitive advantage. The timeline for implementation is rapidly closing. The European Union AI Act is approaching full enforcement in 2026, alongside intensifying SEC scrutiny of material risk disclosures. Organizations attempting to manage these incoming global regulations with manual bolted-on compliance protocols will be unable to compete. They will be moving too slowly to survive in a regulated market. True enterprise AI scale requires building infrastructure that actively accelerates innovation rather than constantly policing it. Establishing transparent, mathematically verifiable AI governance is also the most effective method for securing deep customer trust in an increasingly skeptical market. The organizations that choose to architect oversight directly into their engineering DNA today gain a permanent operational lead. In the coming years, this infrastructure will separate companies that can scale AI from those that are sidelined by risk.